Welcome to ECE 302. This is lecture 3.9 on Poisson random variables. I am Professor Stanley Chen. So this is the fourth random variables that we have been studying in this course. Poisson random variables are very, very interesting in the sense that they are not coming from flipping a coin, like what we have learned in the Bernoulli binomial and the geometric random variables. Poisson random variables actually come from a very unique process which commonly occurs in atoms, electrons, photons. In the modern data science, you have traffics, you have internet, you have networking, you have phone calls. Poisson random variables arrive in those settings. A lot of people think that Poisson random variables are difficult. And in many cases, when they learn Poisson random variable, they tend to just remember the formula. In this lecture, I will try to clarify some of these misconceptions about the Poisson random variable. In particular, I want to show you where does this Poisson random variable come from. I hope that by the end of this lecture, you will not just remember the Poisson formula, but you will also understand how do we formulate the Poisson problem. So to start with, I want to share with you this motivating story. It's about a camera. Everyone knows how cameras take images. Is that when we turn on the shutter, the photon will come to the sensor. And then by accumulating enough photons, we can form a current, and the current will generate a signal. And then by collecting signals in an array of pixels, we form an image. Okay, so this is very, very standard, and we know very well about this process. But how do we map this problem to the Poisson random variable? So let's take a look here. Let's assume that we have an integration time of t. This integration time can be think that you have this exposure, and you turn the exposure on, and then during this period of time, the photon will just come to the camera continuously. During this exposure period, you have these photons. So these yellow dots, they represent the photons. Okay. Now, the photon comes at the arrival rate of alpha, and depending on the brightness of the scene, you may have a higher alpha or you may have a lower alpha. Higher alpha stands for brighter regions, and darker scenes will give you a lower alpha. And so the magnitude of this alpha will determine the density of these photons. So if you have a high alpha, then all these photons, you have a lot more photons that are coming than a low alpha. All right, so now as the photons, they come to the camera, you are trying to record the number of photons. In this process, physics has done experiment, and we are also going to show that the photon arrival process will follow the Poisson process. What do I mean? If you let x be the number of photons that will arrive during this integration time t, then the probability for this x, which is an integer, is an integer random variable, for this x to land on this state k, it means that during this time t, there are altogether k photons that have arrived. Then this probability is given by this magical formula. Now this formula has a parameter called lambda, and lambda is determined by this rate alpha times the duration t. So so you can think as this alpha as the number of photons per unit time, and then this is the total amount of time. And so when you multiply these two together, it would be the total number of photons that you're expecting to see during this integration time of t. All right. So now the key message here is that this Poisson formula. Okay. So this Poisson formula says that the probability of x equals to k is given by this magical thing. This magical thing says that you have lambda to the power k divided by k factorial, and then e to the power minus lambda. And there's absolutely no way that you can just tell this equation from this picture. Okay, so what we are going to do in this lecture is to clarify the origin of this Poisson equation. So if you have ever learned Poisson random variables before, your teacher will probably told you to memorize this Poisson PMF. And then you will learn how to compute the mean and variance and stuff like that. So as I said, what we want to do is we want to ask why Poisson is derived in this particular way and why. Okay, and so in addition, besides this formula, what else can this Poisson equation buy you? And why do we care about so much about the Poisson random variable? And if you have come across some research work in computer vision, you may realize that Poisson random variables are very, very popular in modeling low light imaging. And why is that the case? So we want to go over all these in today's lecture. So this is the outline for today's lecture. We have a few topics here. First of all, we want to talk about the definition of the Poisson random variable. And then we want to demystify a problem that many people, they are not aware of. And even then they pay attention to this problem, they may get confused about this problem, which is the mean and the variance of Poisson random variable. And then we are going to spend some time discussing the origin of Poisson random variable. We want to show that the Poisson random variable doesn't come from the Mars. It's actually well defined according to a physical process. So we want to go over that. Finally, we want to link Poisson random variable with binomial random variable. We want to show that Poisson random variables are actually very good approximations to the binomial random variable. Okay, so to start with, I want to define the Poisson random variable. The Poisson random variable is given by this equation. Okay, so what is this equation? This equation says that the Poisson random variable is a k, and then is taking a stage of k, okay, and the k will go from 0, 1, 2, 3, all the way to infinity. Okay, so I'm missing a 0 in the slide. Now, on the right-hand side of this equation, you realize that there's a lambda. This lambda is called the Poisson rate, okay, or it is the parameter of this Poisson model. Just like the Bernoulli random variable, we have a parameter p, which defines the probability of success. Okay, so this lambda should be given to you ahead of time. Now, once you have this lambda, then everything is well defined because e to the power lambda is a constant. And depending on what the values of k that you're looking at, you can just plug in the k and you can get the right-hand side. So the notation of a Poisson random variable is given by this. You say that the random variable x is drawn from a Poisson distribution with a parameter lambda. You write in this way. There are a couple terms here. X is the number of arrivals. This is the random variable that we are looking at. Alpha is the arrival rate, and t is the time. And usually we define lambda as alpha times t. Okay, so this is the definition of the Poisson random variable. And we also want to highlight the cumulative distribution function of the Poisson random variable. On the left-hand side of this slide, I'm showing you the probability mass function of the Poisson random variable at 3 different values of lambda. Here, the blue stands for lambda equals to 1, green is lambda equals to 4, the yellow one is the lambda equals to 10. As you can see, if you set lambda equals to 1, which is a low value, then most of the probability will be concentrated in the beginning, because when lambda is 1, that means on average you have very few people that will show up, and so the mass will concentrate in the beginning. As lambda goes to a bigger number, then this distribution will go to the right-hand side. In addition, the spread of the distribution becomes bigger and bigger. So that is the PMF of a Poisson random variable depending on the value of lambda. And the x-axis here is the index k. So the the cumulative distribution function of a Poisson, according to the definition, is just the summation of all the states from 0 all the way to k. And when you do the summation, you can see that I'm doing a cumulative sum of my PMF, and that will give me all these curves. Okay. Unfortunately, the CDF of the Poisson random variable is given by this form, and there's no way that you can further simplify. There is one way. The way is to use a thing called the incomplete gamma function, but in many senses it's not much easier than this finite sum. So and this is the a little bit downside of the Poisson random variable, which is that the CDF is fairly complicated. There's no analytic form for this equation. Okay. All right. So here is an example if you wonder how we can use Poisson random variables to solve problems. This problem says that in a telephone call center, the average number of phone calls is lambda calls. Okay, so this is already taking care of the duration time t, which is somewhat embedded in this in this notion. And then you say that x is the actual number of calls, and then you want to find the probability of x bigger than 4 and probability that x is less than or equals to 5. Then what you can do is that you can just calculate the probability by summing the Poisson PMF. For example, if you're looking at x is less than or equals to 5, then you just sum the PMF from 0 to 5. If you're looking at the case where x is bigger than 4, then by the complement, you can calculate the probability that x is less than or equals to 4, and you sum them up, and then you take 1 minus. That would be the number. And clearly, you can plug in the lambda. So if I know lambda is equals to 3, I can just plug in the 3 here, plug in the 3 here, and then you use your computer, then you can get a number. Okay, so that's the example. Now, I want to move on to the second topic, which is about the expectation and the variance, the mean and the variance. I want to first show you the mean and the variance, and I want to point out something that's very, very strange about this Poisson random variable and the confusion that people usually have about the Poisson random variable. Then I'm going to demystify this confusion by showing you some practical scenarios. So what is the mean and the variance of the Poisson random variable? It turns out that the mean of the Poisson random variable is lambda, and the variance is also lambda. Now, how do we show that? We know that the expectation of the Poisson random variable is just the summation of k times lambda to the power k e minus lambda divided by k factorial, k going from 0 all the way to infinity. Now, how do we do this calculation? Well, we know that there is a k here, so you can do the summation of k. K will cancel out with this factorial, so you can remove this k, and then you have lambda to the power k e minus lambda, and then you have k minus 1 factorial. Now, there's a problem here because if k goes from 0, this will be undefined. But never mind. This, if you write it out, it is actually equal to what? Well, it's equal to 0 times this lambda to the power 0 e minus lambda divided by 0 factorial plus k equals to 1 going to infinity, and then k e minus lambda, and then lambda k divided by k factorial. So the first term, when k is equal to 0, this term is actually gone. Okay. So what it means is that you don't have to start with 0. You can start with 1, because when k is 0, this equation says that the k is already gone. Okay. All right. So now, if you follow this, then the remaining computation is not too hard, because here it's just that you can do a substitution. You can say that, all right, I let L equals to k minus 1. All right, and then here you will get L equals to 0, and you will still sum to infinity. And then here you have lambda to the power L plus 1 e minus lambda and then you have L factorial. And so now you can ignore this E minus lambda because this is a constant with respect to the summation. And so all you need to take care of is this. And then this L plus 1 lambda, you can pull the lambda out. And then here you have E minus lambda. And then you just have a simple summation L going from 0 to infinity of lambda to the power L divided by L factorial. And then what is this term? This term is just E lambda. Okay, and then this E lambda will cancel with this E minus lambda, and so you will have lambda. And therefore, we have just shown that this expectation of the Poisson random variable is lambda. Now, if you recall homework number 1, we have actually proved the second moment and also the variance. So if you forget, you can actually go back to homework 1 and look at the solution. If you're still confused, you can ask the TA, how do we prove that the variance is lambda? Okay, so there's a problem here, which is the mean and the variance of this Poisson random variable. So you look at this. You look at this. This is the mean. The mean is lambda. The variance is also lambda. Now, if you recall the beginning when we say that, look, we have a camera. And then the camera is collecting photon. The photon arrival is determined by lambda, and lambda is the brightness of the scene. So if I have a brighter pixel, that means my mean value will be higher, which makes sense, right? Because if you have a brighter scene, and of course, on average, you have more photons coming to your camera, and so that pixel will also be brighter. But the surprising thing is this variance. The variance says that your variance is also equal to lambda. That means if you have a darker pixel, you will actually have less variance. If you have a brighter pixel, you have more variance. Okay, so what does it mean? Well, you have a region, right? So here you have a sun, okay, which is very, very bright, and then here you have a rock, okay. And so let me use a different color. So if you have a sun, which is very, very bright, this is a stone, a rock, which is very, very dark, then when you take a picture, then here it will give you a large expectation, large mean, but also large variance. Okay, and here you have small mean, and then you have small variance. Okay, so what can this be problematic? Well, this is actually a very interesting phenomenon because brighter pixels are brighter, that's okay. Darker pixels, they're darker, that's okay. But this one says that it is noisier because you have a larger variance, so the fluctuation is higher. This one is less noisy. Okay, so this is somewhat interesting. But if you take an actual photo, this is what we are observing. So here you have a very, very dark scenario where we can just set the exposure time of the camera extremely short. So you have very, very few photons that are coming to your camera. You're getting this, okay? Well, correspondingly, this image is similar to you're taking a picture of this rock because it's very, very dark, okay? Here we're just setting the exposure to be short, and so the number of photons that will come to your sensor is few. Here is a very, very bright scene. Okay, you put it under the sun, and then you take a picture. This is much nicer. And so you ask, which one is noisier? Obviously, this one is noisier. So this is very inconsistent with what we have just derived theoretically, that higher lambda will give you higher variance, right? Because if that's the case, then the brighter image should be really noisier, but that's obviously not what we are observing in practice. So this thing does not occur in the in a binomial random variable or geometric random variable or Gaussian random variable. It's not like that. This is very, very unique for the Poisson random variable where the mean and the variance, they are equal. So I want to demystify this misconception that a lot of people have, which is that the Poisson random variable has a higher noise when your scene is brighter. The notion that we sort of tend to miss is this concept called the signal to noise ratio. Signal to noise ratio, of course, as it's called, is the ratio between the signal and also the noise. What is signal? Signal is usually defined as the mean of your random variable, and then noise is the standard deviation of your random variable, which in our case it would be the square root of the variance. So you plug in the Poisson equation. The mean is lambda, and then the variance is also lambda. But don't forget, the noise is actually defined as the square root of the variance, and so you have lambda divided by square root of lambda. And so the signal to noise ratio is actually lambda. Okay, so as lambda grows, and this SNR actually grows. Okay, so you ask, all right, so what? Well, so the message here is that yes, your noise is actually getting bigger and bigger as your signal becomes stronger and stronger. However, the growth of your signal actually overrides the growth of the noise, and therefore the signal to noise is scaled as a function of square root of lambda. And therefore, if you go back to this picture here, here you have a smaller lambda, and then this is a small lambda, so that's the signal, that's the noise. But when you take a square root, this one compared to here, you have a large lambda divided by large lambda when you take a square root. Eventually, this one is still a larger lambda than this case. So this is a higher SNR. This is lower SNR. That's the reason why when you take an image in the brighter scene, you still get a better quality of the image. That has no contradiction with the theory that we're learning in the Poisson random variable, right? So next time when someone says that, well, I'm using Poisson to model a certain scenario, and the noise should be higher because the variance is getting higher, I think now you can tell the person that you should look at the signal to noise ratio rather than just the variance. So I hope I have clarified some important concepts about the Poisson random variable. And then now I want to move on to another very important topic, which a lot of people tend to miss, which is the origin of the Poisson random variable. And I want to emphasize that by knowing the origin of the Poisson random variable, you will be able to formulate a lot more problems than other people. In particular, you will know when the Poisson model will apply and when the Poisson model cannot be applied. Okay, so we want to discuss this topic using a physics point of view. And if you read the ebook, you will be able to see the full derivation. So what I want to do here is to summarize the derivations in a couple slides. So this is the elementary setup. Imagine that I have a camera. Now, if you really don't like camera, that's fine. You can replace this as a bus station, okay? And then here you can imagine that all these yellow dots, they are the passengers. They are coming to the bus stop. Okay, so if you don't like that, you can imagine that here is the airport, a security checkpoint, and these are all the passengers that are coming to the security checkpoint. So this model using a camera is just one of the many possible examples. Okay, so what are the assumptions that we're making here? We assume that during this time t, we have a process x of t, and x of t would define the number of photons that I have observed during this interval t. if I increase the duration by delta t, then the total number of photons that I will observe will be given by x of t plus delta t. Because I have a longer duration time, I should expect to see more photons. There are three assumptions that we are making here in order to understand the origin of Poisson random variable. The first one is that we let t to be very, very small, and then we assume that the difference between this x of t plus delta t and x of t equals to 1. So the probability when you are getting one increment is linearly proportional to alpha times delta t, where alpha is the arrival rate. Okay, so this is a linear relationship. This is very, very important assumption. Okay, the second assumption is that if t is very small, then we assume that there's no more than one electron or no more than one photon that arrives. Okay, so during this delta t, you can either see one or see no. Okay, then so that you cannot see more than one photon. If that holds, then you can take the complement of one minus the other event, because we assume that this interval, during this interval, you are either getting 1 or 0. So if it is not 1, then you have to get 0. That's why you have 1 minus of this probability. If this assumption doesn't hold, then you cannot do this complement. The third assumption is that the number of photons that are arriving, they are not overlapping during the time intervals. Okay, so and then they are independent. This is also a very important assumption, because if they are not independent, then the Poisson equation will not hold. Okay, so we will come back to these three assumptions later. But now let's just assume that these three hypotheses hold, and then we want to show that that will automatically lead to the Poisson random variable. So how do we show that? This involves a little bit of a differential equation, but that's not too hard. Okay, so let me just walk through the step with you one by one. So we want to look at the probability of x of t plus delta equals to k. Okay, so this is the probability that during this time from t plus delta t, what is the number of photons that you're observing? So this can be written as x of t equals to k minus 1, and then there is one additional photon that is happening during this time delta t. So what does it mean? It means that, hey, during this period, I have already got k minus 1 photons, and then during this additional time, I have one more photon. So that would be one possibility. The other possibility is that I have already observed k photons, and during this additional time delta t, I do not have any photon. So during here, I have already got k photons, and then there's no photon that's happening during this time. And so that would give me the second case of ultimately achieving k photons. So these are the two possible cases. And then the first one, I have alpha times delta t, and then the other one, I have 1 minus alpha times delta t. These are based on the hypotheses we just made. So you plug in these two numbers into this equation and you arrange the terms, then you can show that this equation would equal to here. You have x and xt equals to k, and then minus xt equals to k times this number, and then you have this number times that number. Okay. Now, and then you can move the terms around. All these, they're just a very simple algebra. So you move the terms around, you can get to this ratio of x of t plus delta equals to k, t equals to k, delta t, and then on the right-hand side of this alpha times some number. Okay. Now, this quantity should be interesting to look at, because if you set the limit of delta t equals to 0, then this will actually turn to a derivative. Okay, so what do I mean? Well, you look at this equation. If you make the limit of delta t going to 0, of course this would become the slope. And what is the slope? The slope will become this d of this probability. Okay, because you have two functions. You take the difference of delta t, you divide by the delta t, that will give you the slope. So that's the dt of this probability. On the right-hand side is the same thing. Now, to solve this differential equation, right? Why is it a differential equation? because on the left-hand side it is a derivative, on the right-hand side is a function of t. You solve this differential equation for this guy, probability of xt equals to k. You solve that, and then you can find that the solution is given by this equation. This is alpha t to the power k divided by k factorial times e minus alpha t. Okay. Now, I'm giving you this formula, and so the proof will be pretty straightforward. Why? You can just plug this number into the equation, and check if this equality actually holds. And here's the steps. You plug this number in, into here, and then the left-hand side will give you all these, and then you do the chain rule, and you expand the terms, and then you group the terms together, you get this. And magically, this is the same as this formula. Okay, so you can follow this derivation by yourself. You can read this slide more slowly, or you can go to the ebook and read the derivation. The key message here is that the Poisson equation, this magical thing, is the result of solving a differential equation, which is naturally coming from this process. Okay, and if you trace back, and this process comes from this process. This process says that I have incremental events that are happening, and then these are all independent events, and also the probability of that event is linear. So if you violate any of these assumptions, then you won't be able to get a Poisson equation. One scenario would be that you're not just using a camera. Okay, you're not just using a camera to shoot the image, but then all these photons, they are going through some scattering media. So let's say you have a laser pulse, and then you send some photons, and because of all these scattering media, for example, there are water molecules like fog, or you have atmospheric turbulence, or different chemical that are happening in this media, then this photon can go off, okay, instead of just go straight to your camera, okay. So in this case, then some of these assumptions are violated. Then you won't be able to get a Poisson equation. The Poisson equation comes from the fact that everything is simple, everything is linear, everything is independent. Then you will have the Poisson equation. So next time when somebody says that, okay, I know Poisson random variable, you can actually ask, well, where does the Poisson random variable come from? And I hope that this slide can show you that the Poisson random variable doesn't come from the Mars. It's actually coming from a very well-defined physical process where you have these hypotheses being held. Okay, so to just summarize this part of the lecture, we know that the Poisson equation is given by this, and this alpha t, I can just define it as lambda equals to alpha t. Then I will be able to get my favorite Poisson formula. So we have completed 3 sections of 3.9, and now let's go to the last section, which is the Poisson approximation to binomial random variables. This is another very important result. At the high level, it says that binomial can be approximated by a Poisson random variable. If you want to think, how do you want to think this result? You can think it as another way to derive the Poisson formula, which is the limit of a binomial random variable. But I would say that the physics-based approach, which we just went through, is more intuitive than the thing that I'm going to describe. The thing that I'm going to describe is more of a mathematical approximation, which is useful when you are looking at binomial random variable and you want to find approximations. So here's the proposition. It says that if you start with the binomial random variable, and remember that this is the binomial probability mass function, if you set this p to be small, and if you grow this n, okay, and if you define lambda equals to n times p, then this binomial PMF will eventually be well approximated by the PMF of the Poisson equation. Okay, so what do I mean here? It means that this n times p is equal to lambda. Okay, so this is the definition of the lambda in this approximation. For this approximation to hold, you must define lambda as n times p. So if you have a lambda here, now if you make the n bigger, so you grow n, then the p has to become smaller, so that the product will remain a constant. So that's the criteria for this approximation, that you make n big and you make p small. So if everything is satisfied, meaning that you have a small p and a large n, and you really define lambda in this way, then the binomial PMF, which is a discrete random variable, here I'm showing you all these green bars, and the binomial with n equals to 5,000, p equals to 0.01, and that can be well approximated by this blue line. The blue line is the Poisson equation with lambda equals to 50. Okay, so you say, what do I gain from here? You're gaining two things. One is that the Poisson formula is the limit of binomial. Okay, so that gives you the alternative way of defining the Poisson random variable is the limit of the binomial random variable. But as I said, the drawback of looking at this way is that you don't really get the physical intuition, and you don't know under what situation that you cannot model the process using a Poisson. The physical way that we learned in part 3 of today's lecture, which is looking at the photons and deriving the differential equations, that comes from the 3 hypotheses. And so you can verify whether your 3 hypotheses are valid or not in order to understand your problem and see if it can be modeled by Poisson. The binomial approach, it doesn't let you to do so. However, of course, this binomial, once you can prove this result, is a very, very easy thing to remember, that Poisson is the limit of a binomial. The second thing that you can gain from this Poisson approximation to binomial is that is the easy computation. What do I mean? I mean that here you have the binomial random variable, and you have this n choose k. And obviously, this n choose k, when n is big, it's really difficult to calculate this factorial. However, on the right-hand side here, the Poisson equations are a lot easier to compute because lambda, when n is big, when p is small, lambda is usually a reasonable number. Okay, so let me show you one example to illustrate this problem. So suppose you have a data arrival rate n equals to 10 to the power 9 bits per second, and then the probability of having 1 bit error, that is 10 to the power minus 9. You say, okay, in 1 second, how likely we would get 5-bit errors? Well, if you go with the binomial process, then you need to flip the coin 10 to the power 9 times, and then you ask what is the probability of getting 5 heads. That is the number. Okay, so 10 to the power 9 choose 5, and this is probability to the power 5, and 1 minus that to the power this number. And you can plug into a computer. Of course, your computer will not like you because this number is just too big for the computer to compute. It's not the whole number, it's this part, that part, and that part. They're just too big. Okay. Well, now if you plug into the Poisson approximation, you know that lambda equals to n times p, which is 1. And you plug in the Poisson equation, this is this quantity. And this is a lot more manageable. Why? Because 1 to the power 5 divided by 5 factorial e minus 1. How bad can this be? This is just 1 divided by 5 factorial, 5 times, right? So 5 times 4 times 3 times 2 times 1. So this is 20. This is 6. So altogether, this is just 120. E minus 1. E is 2.7. Right, so this is 1 over 2.78. So this number is very reasonable. Okay, So it is a much easier number to calculate, and this is a well approximation to this monster. So how do we prove this Poisson approximation to the binomial? This is not required for our course, but I will still mention it quickly. You can start with this binomial equation, and then you can group the terms together. And here I'm defining a p equals to lambda divided by n because lambda is n times p. So once you do the substitution, and then you can squeeze this lambda to the power k out, right? So now here we have this lambda to the power k. It will go out, and then what? And then you can look at the n factorial, and then you have n minus k factorial. That will give you what? Well, that will give you n factorial, n minus k factorial, and then you have 1 minus n to the power k, okay, because this lambda has gone out. So you have lambda to the power k and then k factorial times this. So here you have n factorial, right? So you have n, and then there's some cancellation going on here. So you have n times n minus 1 times all the way to n minus k plus 1. So that will account for this ratio because all the denominator will be cancelled with the numerator. So the numerator will only have these terms remaining. And then what? Well, and then you also have this divided by n to the power k, which essentially is just n times n times n dot 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 times n, and there are k of these terms, and you can group all these together. Okay, and so when you group all these together, you will see that there is a chain of products like this. In addition, this term can be written as this guy times that guy. Okay, and so now let's take a quick look. This number is going to 1 as n goes to infinity, because as n goes to infinity, this term will go to 0, and so 1 to the power minus k, this will just go to 1. Okay, and then how about this term? This term will also go to 1 because when n goes to infinity, this will just dominate, and so all these terms they will go to 1. So they go to 1, they go to 1, and so the only term that's remaining would be that term and this term. Okay, so you have these two remaining. And so what? Well, and then you go back to our background chapter. You can leverage a result in the logarithm, where the log of 1 plus x is approximately equal to x. And so now you have 1 minus lambda divided by n to the power n. Let's just take a log of this. If you take the log, then you have n times log of this, and then this will approximately equal to n times a minus lambda divided by n. And so now this n will cancel out with each other, so you have minus lambda. And then you take the e back again, so you have this e minus lambda. So what? Well, so this number is going to e minus lambda, and so you have lambda to the power k divided by k factorial, and then e minus lambda. And so we have proved this magical result that Poisson is approximation to the binomial. Okay, so this concludes this lecture, and I know that you will have questions. So please feel free to post your questions on Piazza. Send me an email. I will also encourage you to talk to our teaching assistants, try homework problems, read the ebook, and also watch our homework videos to make sure that you get the idea. Thank you very much.